Ionic bonds are going to be bonds generally made from a metal and a non-metal. Most of the time, the metal is going to be positive, which is a cation, which means that it loses electrons. And the non-metal is going to be negative, which is an anion, which means that it gains electrons. This is going to create a situation where opposite charges are attracted to one another. And so we'll have opposite charges, and they're going to come together to create a neutral ratio of atoms that together form a specific structure. Ionic bonds do not create their own individual little compounds similar to covalent bonds, but they do, if you were to look at them, they would have a particular ratio, such as if we looked at sodium and chlorine. So sodium is going to have 3 electron levels, and in the last one it has 1 electron. The other 2 are full. Chlorine is also going to have 3 electron levels. The last one has 7 electrons in it. So sodium has 3 shells, one being the first 2 being full, the last one having 1 valence electron. And chlorine has 3 shells, the first, again, 2 being full, and the last one having 7 valence electrons. So chlorine has a much higher electronegativity than sodium at 3, and sodium has an electronegativity of 0.9. Electrons are going to want to go to chlorine. They're not going to want to stay at sodium. So what's going to happen is this electron is actually going to leave sodium and join here together with chlorine and make it so that this whole shell goes away, and sodium is now left with a full outer shell, or it meets the octet rule. And chlorine is now going to get another electron here, making that 8 electrons, which also meets the octet rule. So together, they're going to be feeling good as individual atoms. And then what's going to happen is, when sodium loses that electron, it's going to become sodium plus 1, because at the moment it now has 11 protons and 10 electrons. And because of that, it has an extra positive compared to its negative. So it's going to have 1 extra proton, which is going to give it a plus. And chlorine is going to be now -1. And again, because of that, it has 17 protons, and now it has 18 electrons, which is going to make it so that it has an extra negative compared to its positive. So it's going to be a plus and a minus. Now, earlier I was saying that it needed to be neutral. And what you'll notice is when you get the ratio of atoms in an ionic bond, the combination of their charges will equal to 0 if they're bonded correctly. And so if you take a +1 and a -1, that makes 0, an overall 0 charge. And if you were to look at salt, you would see that it always has a ratio of 1 sodium to 1 chlorine, if you were to zoom in on salt and use a microscope. And that is the ratio 1 to 1. Now, when we're naming these, we use a system. So what we do is we, first of all, always just use whatever the first name is. So in this case, you would just use the element name, sodium. And for the second element that's in it, which generally ionic bonds have just a binary compound, meaning that it just has 2 names. For the second element in it, you're going to write the first part of it, and then you're going to add an "ide" to the end of it. So in this case, this is going to be sodium chloride. That is the name of this particular element. And you can find these charges on that periodic table in your notebook, but you can also figure out what they are according to the structure of the element, the Lewis structure. So if we were to look at sodium, we know that when we write sodium's Lewis structure, it has 1 valence electron. And when we write chlorine's Lewis structure, it has 7 valence electrons. Given that, you could logically assume that sodium, and also because it has a very low electronegativity, will lose this one, and chlorine, because it has a high electronegativity, will gain just 1. Now, we can make these sort of ratios with all sorts of elements. So we're going to bond iron and oxygen. So now iron is a tricky one because technically iron has multiple ions that it can make. So let's say we have another iron and oxygen. This iron here, if I gave you the Lewis structure, would have 3 valence electrons to lose. And this iron here would have 2 valence electrons to lose. Oxygen always has 6 valence electrons. That never changes. And so in this case, you could actually have 2 different compounds of iron and oxygen based on the number of valence electrons they have. So we know that this iron is going to turn out to have a +3, and this oxygen is going to turn out to have a -2. This iron is going to turn out to have a +2, and this oxygen is going to also be a -2, just like it was before. Given that, we will have 2 different ratios depending on which ion the iron would make at the time. And this is just something that you kind of have to figure out, generally based on the cation, because that one generally stays the same. It doesn't really change much. So the way we actually do this, the simplest way to make this ratio work, is you take whatever the charge is here and you add that down here to the iron, to the subscript, and you take whatever the charge is here and you add that to the oxygen. So that's going to give us iron 2, as in we have 2 irons, oxygen 3, as in we have 3 oxygens. And if we were to look at our charges doing this, you could take the 2 times +3, and you could take the 3 times -2. You would end up getting a +6 and a -6. And if you take +6 and -6, you get an overall charge of 0. If we look at this side, because of the fact that they have a 2 and a 2, and they are exactly the same charge, we know that +2 and -2 equals 0. So we are going to have 1 of these irons and 1 of these oxygens. So in this case, it will just be FeO. Now, when we're naming these, because of the fact that the irons are 2 different ions, you're going to name this iron, and because it's a +3, you're going to put a Roman numeral 3 here to distinguish that this was an iron +3. And then this would be oxide for the ide that we add to the cation. And in this case, because the iron was a +2, we're going to put iron with a Roman numeral 2, and again, oxide. So our name would be iron 3 oxide, and this would be iron 2 oxide. You only have to worry about the Roman numerals if you have a element that's going to produce multiple ions, which is not all of them.